In this video, we'll look at an example application of the bisection method. After studying this video, you too should be able to employ the bisection method to perform a parametric analysis that involves a roots problem. If you recall from last week, we looked at an empirical model for the population of contaminants in a body of water, given as this linear combination of two exponential functions. At the close of that video, we wanted to generate a graph that showed how the time it takes for the 10 part per million standard to be reached depends on the decay rate of species B. And we saw that it was impossible to solve for that time as some function of KB. We wanted to generate some sort of graph that we thought might look like that. Well, what we can do to get through that roadblock is to formulate this as a roots problem. And if we formulate this as a roots problem and plot it, we get something like this. Here's our roots problem formulation. And our value of the time corresponding that it takes to reach the standard, for in this case KB equals 0.5, would be the root of this function, or where this function equals 0. And we can see that on the graph right here between 4 and 6. So there's our root for the specific case where KB is equal to 0.5. Now what we want to do is we'll first go through a bisection method application to find that root, and then expand that to use this idea to generate that graph of the time to reach the standard as a function of KB. So first let's look at this single application of the bisection method to solve this roots problem, again just for the case where KB equals 5. So this first section of code here just formulates the roots problem and generates the figure that we were just looking at. And then what we need to do is set this up to use the bisection method. And what we'll use is we'll use the basic bisect function, and that was developed in the bisection video. So if you want, you might want to go back and review that part of that video before going further. So we developed that bisection function, and what we needed in order to use that bisection function was to define the function as an anonymous function. Define the roots problem as an anonymous function. So we do that here. So there's our roots problem. And then we have our initial guesses, XL and XU, and then we'll simply call bisection. So there's our function call to the bisect basic function and display the results. So you can run that code and see how it works. The M file is included in the folder with this video. And what I'd like to do is move on to now broadening this analysis to generate a graph of the time to reach the standard as a function of KB. So let's see what we have to modify to do that. So here I've skipped some of the help comments. There's more help comments above here. But here's the code that we can implement bisection to generate that graph. Again, we will set up our parameter values. There's our fixed parameters. And then the parameter that we're studying is KB. So here we'll set up a vector of KB values. And then we're going to pre-allocate some vectors to store our results in. We want to calculate the corresponding value to reach that time, the time to reach that standard value. We'll define that as t standard, and we'll pre-allocate that with the same length as kb so that those two vectors are the same length. And then we'll also keep track of how many iterations it takes for each solution and what is the approximate relative error in each solution. Then all we need to do is use a for loop, and we will do a for loop going with a counter index that goes from 1 to the length of kb, and we are going to go through each value of kb, redefine our anonymous function for each value of kb, and then call that function bisect basic, and we will store the results at the indexed element of t standard, EA, and iter. And I've used one thing that's nice about bisection is we can be pretty sloppy with our initial guesses. So I've just used a large initial bracket that's the same for all kb's, because I know that root is going to fall in between 1 and 20 for all of those values of kb. And then we'll just plot the result. So I would encourage you to run this code in MATLAB, step through it with the debugger, and see how we are building these arrays, these vectors of t standard, EA, and iter. And here's the graph that we get, something like what we expected, and we see that that time comes down fairly rapidly as the decay rate of species B increases, but then it levels off. And if you are an environmental engineer studying this problem, what you might conclude is somewhere around here we're reaching a point of diminishing returns. Basically, the species B is decaying off so fast that it's not a limiting factor on when we achieve that standard. We see that this exponential term goes away, pretty much goes to 0 pretty quick when kb is greater than about 2, and everything is driven by the first term in the model. So making conclusions about the model is kind of beyond the scope, although it's nice to ground what we are doing in some real analysis. What we're really focused on in this video is how we have now used the bisection method to get through that dead end and actually do the parametric analysis that we wanted to do and determine the sensitivity of the time to reach the standard to that decay rate, kb. And again, I would encourage you to step through this code in the MATLAB debugger and make sure you understand how it's working with the bisection method.